Good morning, everyone. Let me know if I'm audible.
Morning, sir.
Good morning.
Yes, sir.
So,
Good morning, sir.
Good morning. Is my screen visible?
No, sir.
No.
No, sir.
Let me see why it is not. Let me know if you can see my screen now.
Yes, sir.
yes, sir. Yes,
Okay.
sir. Yes, sir.
So let's continue from yesterday. We said UDP is basic bare bone, no frills. It primarily does multiplexing and demultiplexing. And for error checking, you include a checksum, and we took an example of what the checksum process is. We did not discuss what are the fields being used in the checksum. That is what we'll discuss now. So what sender does is we've seen the UDP header. The sender treats each segment, including headers, in terms of 16-bit each or 2 bytes, takes all these 2 bytes or 16-bit values, perform a checksum, meaning add them all up, and if there is a carry, add the carry, and then do one's complement, and whatever checksum is computed, it is put into the UDP header. So if you were to look at UDP header, so you have a source port number, destination port number, length, and the data. You compute checksum taking 16 bits at a time. Source port is 16-bit, destination port is 16-bit length, data, and whatever checksum is computed, put into this checksum field. And that is what checksum computation process is. What does receiver do? Receiver will recompute the checksum using the same process that is done by the sender and compare the computed checksum with the checksum received. And the two checksum happens to be same, and if two checksums happen to be same, that means there is no error. If the two checksums are not same, that means two checksum value is not the same, then it is an error and the segment is discarded. If computed checksum is same as what has been received, then no error detected, and that means segment is good and it is passed on to higher layers. It basically is an elementary process, and we'll see that error might still creep in, and we look at how do we deal with. So this is the UDP header, source port number, destination port number, length, and then you put the checksum and of course data in terms of active. While computing a checksum, UDP makes use of pseudo header as well. Pseudo header meaning these are not the header of the UDP protocol. These are the extra information which is used for checksum, even though they are not part of the header. And so, because they're not part of the header, but treated like a header, and this is called pseudo header. Our source IP address, our destination IP address, which are 32-bit each. So you take 16 bits at a time, and then you have a 0 as the filler protocol. UDP protocol is the hex value 11 or decimal value 17, and the length to just make sure that we have 32 bits again, and then compute. And let's look at why do we need pseudo headers. I'll give an example. Pseudo header basically gives you protection against misrouted data graphs. In the next slide, I'll show you how datagram can be misrouted. Further, if computed checksum comes to be 0, then everything transmitted as ones equivalent to 0 ones complement, because all 0 checksum means there is no checksum generated. So initially, it was a choice of the sender whether to include checksum or not. If sender does not want to include checksum, it will put all zeros. If sender want to compute checksum and computed value happens to be 0, then it transmitted as 1. Only special case and nothing else. So let's look at why is that the checksum needs pseudo header and will need a data padding, because remember we are doing checking every time with 16 bit and my data is in terms of bytes, which is 8 bits. So if my data happens to be odd number of characters, let's say 7 or 9 or 11, then I'd be adding one extra byte with zeros, which is called padding bit, to make sure that checksum type I use all the 16 bits. Let's look at the following case, which is called misdirected or misrouted delivery. Let's say machine A is on a network 1, and their machine B and C connected via router, and machine A wants to send a packet to machine B. So what machine A would do, it has some data, let's say computer networks, it's using source port number 2048, which in hex happens to be 0800. It will compute checksum as using source port 0800, destination port 8192, which is in hex is 0x2000, plus data length, let's say 10 bytes of data, 10, and whatever data is, and compute the checksum and put into the header. Now when packets come to router, the router has a buggy software, and while getting a packet to send, it mistakenly changes the IP address from B to IP address C. Now both the machines, the applications running on port 8192, and after changes, it sends out the packet, because router is not looking at UDP data. Router is looking at only IP layer and link layer. So it compute the checksum after changing the IP address, because buggy that will be fine. And then the data packet will be delivered to C. Now C will compute the checksum using source port 2048, destination port 8192, everything is fine. So C would treat packet has been received and passed to application. Whereas actually data has got A wanted to send to B, but because of router's error, it has gone to C and it works fine. This is called misdirected delivery. So how do we deal with? Because router doesn't look at UDP headers, UDP data, and that's why we say we need to use pseudo header, meaning when A compute the checksum, it not only uses the source port, destination port data, it also makes use of source IP address, which is IP address of A, plus the destination IP address. So if A is using source IP address and destination IP address as part of checksum and put the checksum, so even if data is delivered to C because of router bugs, when C compute the checksum, C will take source IP as of A, destination IP of C, because that's what it received. Whereas A has computed checksum using source IP of A with destination IP of B, so checksum at C would fail, and because checksum at C would fail, C would discard the packet. And that's the meaning of misdirected delivery. And that's the reason we include called pseudo headers. Sorry. So you not only use these UDP headers, you use these 12 bytes of extra pseudo headers to compute the checksum and pass it on. And that is
Excuse
what.
me, sir.
Yeah, go ahead.
Sir, can you explain once again?
Yeah. See, UDP header is only source port and destination port. And this information is not there in the book. Let me also tell you that. So to understand what I'm saying here. So UDP header contains only these 8 bytes, source port number, destination port number, length and the checksum and the data. So typically if I am my transport layer, I should use my UDP header, source port, destination port length and data and compute the checksum and put the checksum value into the header. Now, when let's say now A is sending a data to C. So, and B is running an application which is listening on port 8192. C is also running an application which listens on port 8192. But A wants to send UDP data to B. And assuming we are not using pseudo headers, so what A will do using checksum, it uses port number 2048, port number 8192, data length, compute checksum, put it in. A router, when transferring a packet from input interface to output interface, because of bug in software and router, whatever reason, it changes destination IP address from B to C. And the packet is delivered to C. Now, when C gets the segment at the transport layer, it will compute the checksum. If there are no pseudo headers, C would compute the checksum using source port of 2048, destination port of 8192 plus data. Since both B and C having the same destination port, independent machine, so what checksum C would compute and what A has sent, both would match. Both would match, that means C will think packet is right and give the data to the application. So what has happened? A wanted to send data to B, but because the router data has gone to the C, checksum is passed by C and packet is delivered. This is called misdirected delivery or misrouted delivery. And we don't want this delivery to happen because it was never intention. So the safeguard is when A is computing checksum, it not only uses UDP headers, it also uses 12 extra bytes of pseudo headers, which are not part of UDP header, but makes use of extra header information to compute checksum. And those extra 12 bytes are source IP address, destination IP address, protocol which is UDP, which value is 17, and UDP length. The length comes twice. It comes here as well as here, just to make sure we put in 32 bits. And now using pseudo header, so checksum means I'll use the 12 bytes plus this 6 byte source port, destination port, and length. This 18 byte extra and the data to compute the checksum. So now look what happens when A is computing checksum. Now when A puts a checksum, it will use the source port 2048, destination port 8192, source IP of A, destination IP of B, and data length and all that. And checksum would be sent. Let's say router still sends the packet to C because of the error. Now when C compute the checksum, it will take source port 2048, destination port 8192, source IP of A, and destination IP of C because destination IP has changed. Now because C is using destination IP of C, so it will get one checksum. But what is the value A has put in checksum? Using source IP of A and destination IP of B. So that means checksum sent by A would be different than the checksum computed by C. And because the checksum values are different, C would discard the packet. If we hadn't used the pseudo header, then this data packet would have been accepted. And that is what is called misdirected delivery or misrouted delivery. Is that clear?
Yes,
Under
sir.
it was. Okay, so let us do one exercise to compute the checksum. So let's assuming we have a source IP 10.30.26.1, destination IP 10.30.26.11. We use source port number this, destination port number 53, and application data is testing. And I would like you to compute the checksum. So if you look at testing, we write in the hex value, T is 54, E is hex 45, S is 53, and so on and so forth. Now, firstly, do we need a padding here? Look, our data is 7 bytes. And we always take data in terms of 2 bytes. So I need a padding of 0, 0. So even though my length is 7, of the data plus my header length is 8. So my total length is 15. But I need a padding to make it 16-bit boundary. Now I need to include pseudo header. Pseudo header means source IP is given to me, destination IP is given to me, and UDP protocol value is 17 or hex11. Compute the checksum. So if we look at source IP, 10.13, 10 is 0A, 30 is 114, so I get first 16 bits. Then 26.1, I get 10, 26.1, sorry, this happens to be, no, this should be, yeah, this should be 1A, sorry, 16. 26 should be 1A and not 10, 0. So that's a mistake. That's fine. Then we look at 0A14. This is 10.30, 26.11. So I think I made a mistake here. This should be, let me correct it. 26 would be 1A. This is what it should be. You compute, so you have a source IP here, you have a destination IP here, then you have the protocol which is X11 plus length. I have 7 bytes of data plus 8 bytes of UDP header, that becomes 15, so which is 000F. Now I include UDP header, source port number 16384, which happens to be hex 4000, destination port 53, which happens to be 0035, plus, remember pseudo header is length is used twice. So look at the pseudo header. So one is the header in pseudo header length, one is the header in UDP length. So when I compute checksum, length field is computed twice. And you compute whatever value that comes. Your data, which is testing, is TE, ST, IN, G, and 1 padding bytes. Whatever value that comes, add the carry, perform one's complement, and then that becomes the checksum. Assuming you computed the checksum, now let me ask you a question. Assuming I add these 6 bytes extra, UQ to my testing. So rather than data being testing, data is changed to UQ testing. Will that checksum remain same or will that checksum change? Any thoughts? Or if my data is ordered like this, instead of testing, I happen to give you INSTTEG. Will my checksum change? Or will it remain the same? My data has changed. Question is, will the checksum change? Anyone? Anyone would like to answer?
So it will not change, sir.
Why it will not change? Avinash?
Sir, because sir,
I'm changing my data. Your answer is right, it will not change, but give me the reason why.
sir, just we are altering the message, sir. That's why.
So that means I can alter the message, checksum shouldn't change. What happens if I were to do other way out? Instead of, I would have simply put T at the end. Will checksum change? Let's say my data
No,
happens to be not this. Instead of this, if I were to make data as if I made my data as this, I just move T at the side. Will my checksum change?
No, sir.
It will change.
So why, sir?
That's what I tried to ask you. So why don't you guys work out, take the values, compute the checksum yourself. I leave it as an exercise and send me find out the answer. And if not, then we can work out as exercise. Maybe we run a tutorial class to tell you why it doesn't change. So you do yourself manually, compute the checksum for this data, compute the checksum for this data, compute checksum for this data, and see in these two cases it won't change, in this case it would change, and then find out why it does not change for these two, but it changes for this. Spend your time and let me know if you can't figure out. Then I can answer you. So take as a home exercise. Okay? Is that fine, Avinas?
Yes, sir.
So class try doing an exercise and see how does it work. So to summarize, UDP is a transport protocol. It does multiplexing and demultiplexing. That's the core job. And a message delivery, because it doesn't do any error control. It does error checking, whether packet is corrupted or not, or does not do error control like congestion control or flow control or retransmission, anything of that kind. That's why it is also called bare bones or glorified IP or no frills transport protocol. No frills means there are no extra heading. And it is quickest delivery. So if network is congested, UDP might cause more congestion, will keep on sending data. We looked at transport layer as connection oriented. We also said what do we expect from the transport layer? The services, transport layer, it does not provide, it gives me reliability. If you look at TCP, it can give me order delivery, it can give me packet which is not corrupted, but transport layer cannot guarantee me throughput. Transport layer cannot guarantee me delay. Transport layer cannot tell me your data would always be delivered in, let's say, 1 minute or 1 second or 10 seconds, whatever. It will try to deliver, yes, based on network, but it cannot guarantee you. Like I took as an example, any courier company, even though claim we guarantee you to deliver in 24 hours, but there is no guarantee. All that they do is if they can't deliver, they'll give you money back. But that is not a guarantee. So their damage is limited too. If they don't honor the commitment, will give you the money back what you paid. If you're sending a check or exam paper and you registration and you delayed by late, registration failed, they pay you some 100 rupees back, but you lost a whole year. So transport layer does not provide any guarantee for throughput. Transport layer does not provide any guarantee for delay. Transport layer does not provide any security either. Whatever security we're looking at, SSL, HTTPS, that is on top of transport layer. So some people think SSL is part of transport layer, but for all practical purposes, it is part of considered as application layer. Then we look at UDP protocol. Is basically simple headers because of multiplexing, demultiplexing, and uncorrupted message delivery. If it delivers, it can lose packets, it can deliver out of order, but deliver correctly. So it has a very minimal headers, source port, destination port for your multiplexing, demultiplexing, length to only the message boundary, and checksum to make sure that it can check is packet corrupted or not. And that is what UDP does. Now we start with reliable transport protocol because UDP is said to be unreliable in the sense packet could be lost or packet could be reordered. So if you were to do reliable delivery, let's start with what reliable delivery means. We'll make certain assumptions and then we'll, based on the assumptions, we will look at how do we proceed. So build a basis of the reliable data transfer. What is involved? We start with very simple case, assuming there are no errors in the underlying channel network, and then we slowly introduce errors and see what is that the transporter needs to do to provide. So you know what it means and how TCP has evolved, because even some errors introduced, a lot of work has to be done to deal with the errors. And this primarily because of the reliable data transfer, it is one of the top 10 list of important topics in network. How to deliver data correctly, properly, in order, so that receiver could be sure that data has been delivered. So our model would be something like this. We had application layer. In the application layer, we have a sending process and a receiving process. So sending application will give data to the transport layer. Transport layer would make use of underlying network, because transport layer is end-to-end. So transport layer has to make use of network layer, and transport layer will give data to, it will segment the data, give it to network layer, and network layer will transmit. Now transport layer has no control over this network layer channel, or what is called network channel, which could be completely unreliable, which could be reliable. This network layer could corrupt the packet, it could make out of order, it can lose packets, it can duplicate packets, it can do whatever it needs to be. But when transport layer says, I'm going to deliver reliably, it has to take care that if my underlying network channel creates some troubles or creates some errors, how to deal with those errors. And processing those cases, what basically makes transport layer or TCP more complex. So this is the model we start with. So basically we look at how good our reliable or unreliable channel is. So we'll start from assuming that our channel is completely reliable. That means it does not do any error and it guarantees delivery. A very, very ideal case that does not happen in real life. Now from ideal case, we'll slowly introduce the errors. And once we introduce the errors, then we look at how does transport layer does to make sure that to the application, it delivers data reliably. Reliably meaning it delivers in order, without duplication, error free. And that's the meaning of, and if any data is lost by network channel, the transport layer who has to retransmit. Once it get the data, once my transport layer get the data from the sender, it is the transport layer headache to send it out. If network layer corrupts it, it will retransmit it, loses it, it will retransmit it. It will not tell application, hey, I lost the data, please send me again. That would not happen. So that's the purpose of building a reliable data transfer. So what is involved? We would have an application, and assuming my transport layer gives me basically 4 APIs. One is called RDT send, that is reliable data transfer send. So application invokes this API RDT send and gives the data to my transport layer. Now sending side want to give, so sending side says to the application, once you give me data, I ensure you the data will be transferred reliably. And what does that mean? It has to do whatever it needs to do, its own error checking, own control and transfer. But it is depending on the unreliable service. It's something like, as a HOD, I give to my office admin saying, please transfer, send this packet, send this paper to the other department. And now it is my office admin responsibility to send this paper reliably. And I'm done. Now it may so happen that our office admin calls the attendant, we just say give it to the other HOD, other department. Now the attendant may simply vanish after taking the letter, may simply leave the college, never delivers. Then office admin has to make sure that what happened, has the letter been delivered to other end, or a timeout has occurred. If not, it will make a copy of it. So it has to keep a copy. Because if the underlying attendant has left and throw the packet away, it will have to make a copy, make a new copy, take another attendant, send it out, till it get the confirmation from the other office admin that it has been received. And then that will happen. So same way, my transport layer, when it get the data, it has to keep a copy and then sends it out, assuming my channel console loses it. So depending on how my underlying channel behavior of transport layer would change. So we'll start with simplistic cases of saying my channel is reliable, and then we build errors. So what the APIs are? Application invokes RDT send, that is reliable data transfer send. Now this transport layer depends upon my unreliable channel or network channel. So it will invoke the API called UDT send, unreliable data transfer, and give to reliable channel this channel. Channel will deliver the packet to the other end. So transport layer would invoke RDT receive, reliable data transfer receive, and receiving from the network, and then it deliver data to the application, where the API will basically look at. And then, so basically when unreliable channel get the data at the other end, invokes the API RDT receive, gives it to the transport layer would basically invoke deliver data and gives to the application. So we'll start with very, very simple case to look at how data transfer really happens. So we'll assume that my channel is completely reliable, very, very idealistic case does not happen. We'll also look at data transfer in one direction, sender to receiver, to understand the working of reliable channel. Even though data transfer can happen both places, when you use TCP, data transfer happens in both places, process is the same. So to understand the working of reliable channel, we'll consider data transfer only in one direction, but we'll have control messages which could flow in both directions. And we'll make use of finite state machine. I'm sure you love your topic of automata theory, which you studied last semester. And in case you have forgotten, I would strongly recommend you or appeal you, please revise, revisit automata theory, the very first part called finite state machines. We will not go to non-deterministic automata, we will not go to Turing machine, we will not go to push down or regular expression, but just revise your finite state machine, which you were studied in the early part of your automata theory course. We'll use that to determine, in fact, anytime you build network applications, which is event driven, and if you can make an automata for the sender side, if you can make an automata at the receiver side, and if you make sure that you have taken care of all the event and action, then your design is perfect. In fact, if you have, let's say, 1 month to build an application, I would say spend 20 days in perfecting your finite state machine automata with event, actions, everything. And once your automata is through, use only 5 days to implement and 5 days to test. What we do is the other way out. One day we write the requirement, start coding second day itself, and then we keep on coding for the rest of our life. So make a right design, and that's the role FSM plays. So understand that part. So we look at what would happen. We know the finite state machine we represent by a circle. Then there is an event. When event happens, we take an action and change the state. So from some state, a event occurs, we take some action and go to another state. So this is how we represent. If we go to different state, we put in different state. If we go to same state, we put a as to itself. And that's the notation would basically use finite state machine. So we're not doing non-deterministic, we're doing deterministic finite state machine. And we'll use that to build and understand how does my reliable data transfer is done by my transport layer using the underlying channel. So first we look at the case that my underlying channel is perfectly reliable. That means if my transport layer gives data to the underlying channel, it will not corrupt any errors, it will lose any packets, and it guarantees order delivery. It's a very, very idealistic case, which doesn't happen, but assume that to understand how simplistic my transport layer could be. And then we start introducing errors. So assuming my underlying channel does not introduce any bit errors, does not lose any packet, and delivers packets data in order, then how does my finite state machine for sender and receiver would look? So what happens to the sender? What happens to the receiver? So typically what happens to the sender? Sender will get the data from the application, send the data, and because my channel is not losing a packet, it is not corrupting a packet, it is delivering in order. That means once data is given to the underlying channel, data would be delivered. So I don't have to worry about any hack or anything of that kind. So my transport layer state would be one. I'll wait for the data from my application. When I get the data from the application, which is application calls RDT send. That means an event has occurred where application invokes my API and give me the data. Now, once I get the data, what do? I make the packet for my underlying channel, and using that API of the underlying channel, UDT, I send the packet. After sending a packet, nothing else to do because my underlying channel has guaranteed me that there will be no bit errors, there is no loss, and delivery in order. So that means I can wait for next packet from the application. So I go back to same state. So if my underlying channel is guarantees me everything, I receive the data from application, which is an event. I make the packet for the network underlying channel, invoke the API for the underlying channel, and because of this, data will always be delivered. I go back and wait for next event from the application. And that's all is my state machine for the sender. What would be my state machine for the receiver? This is state machine for the transport layer. So that means when the underlying channel get the data, it will invoke my API called RDT receive. So I'm getting the data from my underlying channel. It gives me a network layer packet. And because my underlying channel has guaranteed me that there's no bit error, there's no lost packets, order delivery, so I know the data is correct. I simply extract the packet and give the API which goes to the application. And what does my receiver do? Wait for the next packet. So if my underlying channel is perfectly reliable, does not cause any kind of errors, this is my state machine of sender, this is my state machine of receiver. Any questions on this part? Because you are going to build upon this for other cases. Any questions? No questions? If no questions, let's continue. Now assuming that my channel does some error, it can corrupt the bit errors. It does not lose the packet, but it can corrupt the packet. So a bit 1 could become 0, a bit 0 could 1, but it delivers in order. It does not lose a packet, but it can corrupt the packet. Now, if corrupting a packet, sender does not know because sender is given data to the underlying channel and receiver would deliver, the underlying channel would deliver to the receiver. So how would receiver know that packet is corrupted or not corrupted? What should we enhance the transport layer protocol so that receiver can know whether packet is corrupted or not corrupted? Any thoughts? When my channel is delivering packet and channel says corruption might happen, so what we need to do in our transport layer to make sure that receiver is able to detect that there is a packet corruption or no corruption?
Sir, if the received data is acknowledged by the receiver that it is
But how
corrupted.
does receiver know? How does receiver know data is corrupted or not corrupted? I'm sending only data.
So it
So
has
what
to
we
use
need to
some
do,
corruption detection.
so we need to add some extra checksum to the
Check.
data, okay? Because unless we add the checksum or some CRC or some field, receiver would have no clue. So that means in previous case, if you look at when my channel was reliable, I'm sending a packet and not doing any checksum. So that means when I make packet, my packet should include data and the checksum also. And the receiver could do the checksum. Okay. Now receiver could do checksum and know whether it is packet is corrupted or not corrupted. If packet is corrupted, then it will say NAC, no, packet was corrupted. If packet was not corrupted, it could give you an ACK. Assuming this being the case, so sender will include the checksum along with the data when it's sending to the underlying channel. The receiving side, it will compute the checksum, compares the checksum, find out if packet is corrupted or not. If it is corrupted, it will send an NAC. If it is not corrupted, it will send an ACK. So how does my state machine will look like? So we need error detection. We also need receiver feedback because sender needs to know, should I need to retransmit or should I receive a next packet? So how does my state transmission or my FSM would become for the receiver, for the sender and for the receiver? When you do a phone call, talking to somebody and noise introduced, what does the receiver say? Hey, couldn't hear, please repeat. And then sender repeats. Same way, if my receiver says NAC, I did not get the packet properly, sender would resend. So how does my FSM look like? Previously, we had no control messages, but just doing data and nothing else. Now we introduce two messages called ACK and NAC. ACK means data received correctly, NAC means data received corrupted, and because we are doing ACK and NAC, any protocol, and NAC automatically means it has to be repeated. So NAC implies sender has to repeat the packet. That's why it's called this protocol that use ARQ is also called ARQ protocol, meaning automatic repeat request. If you get a NAC, please retransmit the packet. NAC meaning retransmit, and that is what it basically means. So ARQ protocols requires error detection and retransmission if packet has been corrupted. So let's look at my FSM for sender and receiver. Now let's look at the FSM is waiting for above. Application invokes the API, send data. Now what is the action? It makes packet with data and the checksum, and that is my send packet. And send the packet using my underlying channel. After sending it, does it come back to same state or does it need to go to different state? Any thought? After
Sir,
sending this
it
packet,
depends.
why should go to different state? Because it
Sir,
has
if
to
the
wait for
data,
ACK or a NAC.
yes,
It
sir,
has
if
to
it
make
gets
sure
hacked, then it
whether,
will send.
yeah, whether it has to resend or data is correctly received. So it basically goes to a state which indicates wait for the ACK or a NAC, means wait for the packet from unreliable channel. This state I am getting data from my application. This state I am getting packet from my unreliable channel, underlying channel, which would be either ACK or a NAC. Now, if I received is a NAC, what I need to do? I received a packet which is an event, and I looked at the packet happens to be NAC. What is my action? Resend the packet was already made. I resend the packet and I resend the packet. Should I go back to same state or should I go back to previous state? Any questions? Any input? Kavita Chaudhary, should I go back to same state or should I go back to, so should I go back to this state or should I go to previous state or another state?
Previous states.
What happens if this packet is corrupted again?
Sir, we
However,
have
so
to send it, sir.
but if you go to this state, we are waiting only, we know that data is set. We are waiting from the application above. So till
Sir,
I
so
get an act, I have to remain in this state. I'm resending it. The resending could be corrupted again. I get an act again. I resend it could be corrupted again. So till I get an act, I will remain in this state. So once I get the act, I know data has been received correctly by the other end, and now I can get the data from the application. I do nothing. I got the act and go back to state, waiting for the data from my application. Any questions about this part? Because this is crucial and we are going to build upon this down the line. Amravati. Would you like to answer? Bhagwat Gautam. Any questions about this? Because you're going to get more and more complicated. Chatra R or Chatra K, would you like to answer? Dhananjay?
sir, no doubt, sir.
No doubts? Okay.
No, sir.
Assuming
Sir, I have
understood,
doubts, sir.
go ahead, tell me. What is the doubt?
Sir, why it is remaining on the same, sir? Why it is not going previous?
Let's look at here. See, I got the NAC, I send the packet again. What happens if the packet is corrupted again? I get the NAC again. See, I need to,
Yes, sir.
what is the job of transport layer? Job of transport layer told to application, I will deliver guaranteedly at the other end, reliably. Now, how does it, this my underlying channel says that I'll corrupt only one packet, not the second packet? It didn't say that. It says I can corrupt packet anytime. All the underlying channel telling is, I will not lose the packet. I'll maintain the order, would not lose, but I can corrupt the packet. So if I resend, this packet could be corrupted again. And whenever this corrupted packet is delivered, the receiver would send the ACK or an ACK. If I get an ACK, I need to resend. So I need to keep waiting here till I get the ACK, because then only I'm sure the data is delivered, and only then I wait for the get the packet from the above. So till I get the ACK, I'll remain in this state. Avinash, is that fine now?
Yes, sir. Right now, understood, sir.
Now can you build a state for the receiver? Would receiver have two states or receiver would have one state? So what happens to the receiver? Receiver underlying channel called RDT receive, delivers the packet. Now when receiver gets the packet, it could either be corrupted or it could be uncorrupted. There are only two choices. If packet is corrupted, what does receiver do? Sends the NAC to the other end and done. And waits for the next packet. If packet is not corrupted, what does receiver do? It will send the ACK and deliver the packet to the application. If it is not corrupted, it will extract the packet, deliver the packet to the application and send the ACK and wait for the same state. So receiver has same state, no two states, whereas sender has two states. So just because we introduce bit errors, sender FSM move from one state to two state, where receiver is only one state. Are we clear here? So let us look at things in operation. How does it work? Let's look at a use case where there is no error. How does communication happen? And look at the case where there is error. Then how does communication happen? So this is starting state. The starting state for my receiver. So application invokes RDT send. So event occurs for transport layer. It makes a packet, including data received from application, plus its own checksum. Checksum is not given by the application, and send the packet and goes to the state. So it sends the packet to the other end and goes to the state of wait for this. Now this packet is received. So my underlying channel gives this packet to my transport layer, and this packet is not corrupted. The packet is not corrupted, it will simply send the ACK, and from network perspective, and it gets the ACK, because get the ACK, the fellow goes to base state. Now look at the case where packets gets corrupted. So what happens? Look at the same case. I get the data from application, I make the packet with data and my own checksum of the data and send the packet. Packet is sent and I go to this state. Now my underlying network channel has corrupted the packet. Because looking at the case of errors. So underlying channel invokes RDT receive, and by using checksum, my transport at the receiver determines that packet is corrupted. If packet is corrupted, what does receiver do? Sends a NAC. And NAC would come to this state. It sends a NAC. Now because it sends a NAC, my transport at the receiver gets the NAC. Because it gets the NAC, it sends the packet again. So we'll assume that when it sends the packet again, this time there is no corruption and packet is delivered. When there is no corruption, underlying channel invokes RDT receive, gives the packet to transport layer. Transport layer compute the checksum and compares and sees packet is not corrupt. So it extracts the packet, gives to the application and sends the ACK. When it sends the ACK, now receiver knows, sorry, sender knows data has been received correctly, and then it waits for the state back to waiting for the next packet from the application. So this corrupted case, when data is sent, it received correctly. If there's error again, this cycle will keep on going and get the ACK, and that state changes. And then, so while in this waiting for the ACK or NACK, my transport layer does not get any packet from application. If application sends, it will lie in the queue. I won't even look at it. The sender may be blocked. So this is how this protocol, so we started with RDT 1.0. RDT 1.0 means completely reliable channel. Then we say we introduce an error called, my underlying channel could introduce bit error, but a more realistic scenario, and we call RDT 2.0. Now, is there a problem with this RDT 2.0? Design a protocol. Does this protocol work correctly? Answer is no. There's a serious flaw in this protocol, and we'll look at why the serious flaw. This kind of protocol also called stop and wait, because I wait for the ACK, till I get the ACK, I don't do anything. And that's why such protocols are called stop and wait, because once I send the data, I wait for the ACK, till the ACK or an ACK comes, I don't do any action. And that is what called wait and stop and wait protocols. Yes, there are serious issues. It is a basic flaw. And basic flaw is what happens if ACK is corrupted or NACK is corrupted itself. Because we did not introduce any checksum the ACK or a NACK. Now it may so happen that receiver sends the ACK, but network corrupts the packet and ACK becomes a NACK. Or receiver sends the NACK, and because of corruption, NACK becomes the ACK. Will the protocol work? It would not work. And that is what we'll study next lecture. So when the packet is corrupted, when the ACK and NAC is corrupted, how does my transport data deals with it? How does my state transition become? So I would like you to look at the case. So look at what happens. I basically what is called send the packet, receiver sends me the ACK because receiver received correctly, but channel has corrupted the packet and ACK becomes the NAC. So I'll resend the packet. And receiver does not know it is a duplicate or it is the original. So that means we need a mechanism to distinguish between original and duplicate. So look at all those mechanisms, and that is what we'll study is called RDT 2.1, making changes. So 2.0 has a serious flaw in that sense. Receiver can discard the packet or receiver may not receive a packet. Because if receiver sends a NAC and channel corrupts it to make a NAC, I will not resend a packet. So receiver never receives a packet or receiver can receive duplicate packet. So these are the cases that may happen. So in that sense, RDT 2.0 is not perfect. It has a flaw, design level flaw, not the implementation flaw. And we look at how to deal with these numbers. And that is what we'll study next. So we'll look at modifications to the protocol 2.0, how do we deal with corrupted ACK and NAC, and how do we deal with the duplicate delivery or lost delivery. If any questions, let me know. Otherwise, we can disconnect and close. Any questions? If no questions, then we can stop.